Welcome to CSI Training. Our mission is to impart the information, techniques, and confidence to successfully apply RBM, reliability-based maintenance technologies and products. Thank you for joining the thousands who have recognized and selected CSI Training as the world leader for quality instructional products. This program, Belt Drives, takes you with us inside industrial plants to check belt-driven machines, showing you many strategic techniques for diagnosing and correcting a wide variety of belt problems. You will learn how to make a quick analysis of vibration data to confirm belt problems. You will learn how to use simple tools to measure and correct the most common and costly belt problem, misalignment. You will learn how to transform those growling beasts into purring kittens. Let's take a look at a case history of a belt-driven pump to see just how much energy can be added to this system from the belt drive and how a few corrections can drastically reduce the vibration from the belt drive. This high-resolution spectrum is from the sheave end of the motor in the horizontal direction. There are only 3 peaks, with the smallest one being the speed of the pump. The next one is motor turning speed, but the largest peak is belt-related. Notice that the amplitude of this peak is 1.2 inches per second, a critical amount of energy for any machine. The total energy in the spectrum is 1.38 inches per second, meaning that this belt problem accounted for more than 85% of the total energy in the system. Some corrections were made to the belt drive that included replacing the belts. This spectrum was collected after the belts were replaced. The peak due to the belt-related problems was reduced by a factor of 12. However, this is still too high for belt drive vibration, and additional work should reduce this amount by at least half. In another section, we will look at the cause of this belt-related energy and the steps that can be taken to correct it. First, let's take a look at belt design and their operational characteristics. It is important to know the design of belts and to understand their operational characteristics in order to better recognize and correct belt problems. Belts come in many shapes and sizes to accommodate most power transmission requirements. The V-belt is the most common, while variances to it are used in special applications. V-belts can operate at speeds up to 6,600 feet per minute, while a cog belt and a ribbed V-belt can run much faster. But they all operate on the principle of friction. The V-belt has straight sides, but as it has been around the sheave, the bottom half of the belt compresses, causing the sides of the belt to bulge and wedge tight against the groove walls. And while the bottom half of the belt compresses, the top half is in tension and stretches. The center part of the belt is the only part of the belt that does not change shape as it passes around the sheave. This part is reinforced with cords. The cords enable the belt to carry loads. Depending on the load to be carried, the cords can be rayon, nylon, glass, polymers, or even steel. There can be one row of cords or several. These cords are encased in a harder rubber for strength and to keep the cords from migrating to other regions of the belt. A variation of the standard V-belt is a cog belt, which allows more flexibility in the compression section of the belt, allowing it to be used on smaller diameter sheaves. A cog belt can run at higher speeds than a standard V-belt of the same size. Another variation of the V-belt is the ribbed V-belt, which tends to run quieter and can be used at speeds up to 10,000 feet per minute. It is wider and thinner than a standard V-belt and has many small V's that ride on a specially designed sheave. This is the only type of V-belt that should ride in the bottom of the sheave. The banded belt is used in place of multiple belts. It is several standard V-belts that have a common back. The benefits over multiple belts are, it will be a matched set. There is no lateral movement of the belts. There is no belt turnover, and the slippage is the same for all the belts. This belt is a double-sided V-belt, which is essentially 2 single V-belts molded back to back. The double V-belt is used on drives with reverse bends, where power is transmitted by both sides of the belt. When exact speed is required and no slippage can be allowed, a timing belt or positive drive belt can be used. It has special teeth similar to gear teeth and must be used over a matching gear-toothed sheave. There are 3 industry standards for measuring belt length. Fractional horsepower L-series belts use the length of the outside as their numbering system. For example, a 4L215 belt is 21.5 inches long around the outside measurement. The A, B, C, D series belts use the inside length as the numbering system. For example, a B48 belt is 48 inches along the inside length. It will be 51 inches along the outside. The 3X, 4X, 5X series belts use another length measurement for their numbering system. It is the pitch length. The pitch length is the distance along the belt in the region of the reinforcing cord. This length is considered to be the nominal length of the belt. Pitch length is the length that should be used when making any belt calculations. Sheaves also have 2 standard measurements. One is the outside diameter and the other is the pitch diameter. The pitch diameter is the diameter that would be measured across the sheave to the pitch line of a belt in the groove. This pitch diameter is the measurement that should be used when making any belt calculations. Belt drives are friction drives and depend on friction between the belt and the sheave to transmit power to the driven sheave. However, friction generates heat, and heat is the #1 enemy of belts and belt life. So there's a fine line between just enough friction and too much friction. The ability to transmit power depends on friction, belt tension, belt wrap, and the speed of the belt, usually measured in feet per minute. The presence of oil, grease, and heat damage belts and are the most common sources of efficiency losses. The friction is affected by belt tension, which must be enough to force the belt into the groove and hold it tightly against the groove walls. The belt must not bottom out in the sheave, because the sheave then pushes the belt out and away from the groove walls. The proper belt tension is the least tension that will keep the belts from slipping. More tension accelerates the wear on the belts and sheaves and puts extra load on the bearings, shortening their life. When the sheaves are still, the tension throughout the belt is constant. As the drive sheave rotates, it pulls on the belt, increasing belt tension to the driven sheave. This is often referred to as the tension side of the belt. The belt on the opposite side, or the following side, then tends to be somewhat looser and is called the slack side. When there is excessive load on the belt, the difference between the tension and slack side can cause the belt to pull away from the sheave and allow the sheave to slip. This is called belt slip. Belt slip generates tremendous heat, causing slip burn on the belts, which substantially shortens belt life and wears the sheave. Belt slip occurs in all belts except the positive drive timing belts. Another condition that results from the high loading of belts is belt creep. Since the tension side of the belt is stretched, the driving sheave receives more belt than it gives out. This difference creates relative motion between the sheave and the belt, which is referred to as belt creep. It is present in most belts, except those which have internal cords that don't stretch, such as in the case of steel-corded belts. Even under the best conditions, belts slip, and in multiple belt drives, they slip and creep at different rates, generating excessive amounts of heat. Belt wrap affects the friction and therefore the efficiency of your belt drive. Belt wrap, or the arc of contact, is the distance around the sheave that the belt contacts the groove. The greater the belt wrap, the greater will be the friction. The best belt wrap is a 180-degree wrap, which can only be achieved with a 1-to-1 ratio. But a 1-to-1 ratio is the worst ratio from a vibration standpoint, and most of your power transmission requirements are not a 1-to-1 ratio. This ratio of 5-to-1 has much less belt wrap and will therefore have more belt slip. A ratio greater than 3-to-1 is not recommended. A ratio of 3-to-1 has acceptable belt wrap when the center-to-center distance is great. But if the sheaves are close, the belt wrap is substantially reduced, decreasing friction and increasing belt slip. If a higher ratio is required, use a stepped drive with an intermediate shaft. The fourth variable that affects the belt's ability to transmit power is the speed of the belt. This is usually measured in feet per minute. That is, how many feet that a position on the belt travels in 1 minute's time. Typically, the faster the belt is moving, the more efficient the system is, and the less tension is required. However, there are some inconsistencies here that must be compensated for. For example, as the belt rotates faster, centrifugal force pulls outward on the belt, pulling it away from the sheaves and increasing the possibility of belt slip. Belt drives can be very efficient with efficiency ratings above 95%. But in proper tension, belt wrap and speed can reduce the friction and severely reduce the efficiency. From a vibration viewpoint, not all belts are created equal. Some types, due to their design, generate more vibration. Here we provide a listing of the belt types, grading them on a scale of 1 to 100, with 100 being the smoothest and quietest operating from a vibration standpoint. Topping the list with 100 points is the endless woven flat belt. A big gap exists between this belt and the next, which is the poly V belt, rated at 60 points. The link belt, without rivets, is third with 50 points. The riveted link belt follows at 40 points. The wide-angle V belt is rated at 30 points, and a timing belt is rated at 25 points. The multiple V or banded belt comes in at half that, or 12 points, and the standard V belts are near the bottom at 10 points. The lowest rated of these belts, the standard V belt, is the most common in industry, partly because it will stay in the sheave and transmit power with minimal effort on our part to provide precision operating conditions. To upgrade to the poly V belt, for example, means replacing all the sheaves in a drive and ensuring precision sheave alignment, because the poly V belt is less tolerant of sheave misalignment. The costs of dollars and labor to upgrade can make it prohibitive. As new machines are designed and added in the plant, they should incorporate some of the best power transmission sources. Earlier we mentioned that heat is the #1 enemy of belts. The belts should not run in applications where their temperature will be over 140 degrees. The cooler the belt runs, the longer will be its useful life. Belt drive guards should be a cage type with plenty of airflow to cool the belts. Solid enclosures trap heat, causing the belts to overheat, shortening the life. One drawback to the banded belts is they tend to run hotter because the band traps the heat, not letting it dissipate. Belts have a design life of 25,000 hours, or about 2 years and 10 months. Sheaves have a design life of 5 to 1. That is, they should be replaced or reworked after every 5th belt set is used. In industry today, it is common for belts to wear out much sooner, but it is assumed that the sheave will last indefinitely. When belts do not reach their expected life, the cause can be due to poor design, poor installation techniques, or even due to worn sheaves. Each belt problem has particular characteristics that will show up in vibration data. Here, we will look at many common problems and how you can recognize them in vibration data. Another section on belt installation shows how to correct these problems. The most common belt-related problem is a misalignment condition. The sheaves can have angular misalignment, offset misalignment, or any combination. With any type of misalignment, the belts ride up on the groove wall and slap back into the groove, repeating a cycle of riding up and slapping back into the sheave once during each shaft rotation. This produces a constant pulling against the side of the sheave, which is along the axis of the shaft. The rubbing and pulling against the sheave generates excess heat and wears both the belt and the sheave, drastically reducing belt life. In extreme misalignment, a belt may roll over in the sheave or actually ride out of the sheave. If misalignment is greater than 1/16 of an inch for each inch of center-to-center distance, very rapid wear will result. In multiple belt applications, angular misalignment causes some belts to be tight and others loose, so that they flap and slip, carrying less load than others. The axial motion of the shaft due to misalignment appears in spectral data at 1 cycle per shaft revolution of the shaft being measured. For example, measurements taken on this motor would have a high peak in the axial direction at 1800 cycles per minute. Axial measurements on the fan will have a high peak at 1100 cycles per minute. Let's look at the data from this fan as an example. During the checks prior to balancing this fan, the vibration data collected in the axial direction on the motor showed a 1 times peak greater than 1.1 inches per second. On the fan, the initial vibration at fan turning speed was 0.5 inches per second. A quick alignment check was made, and the sheaves were found to be more than 1.5 inches out of alignment. When the alignment was corrected, the axial measurement on the motor reduced to 0.02 inches per second. The vibration due to belt misalignment was reduced by more than 55 times. The axial measurement on the fan reduced to less than 0.06 inches per second, or a reduction of nearly 10 times. Another point of interest on this fan was that prior to correcting the belt problem, the coast down was less than 7 seconds long. But after the belt correction, the coast down was well over 2 minutes. This effect, combined with the vibration measurements, clearly indicate that the misaligned belts consumed massive amounts of energy and produced much more friction than necessary for the machine to run optimally. Defects on belts can be cracks, splits, or like this, may have chunks missing from the belt. Any of these defects on a belt bump the sheave as it rolls onto it, generating a pulse that can be measured with a vibration sensor. Since the defect bumps both sheaves during one circuit of the belt, there is a peak in the spectral data equal to 2 times the belt rotational frequency. This belt rotational frequency is usually referred to as belt frequency and can be defined as the number of times per minute that a belt makes one complete circuit. Since the circumference of the belt is much larger than either sheave, it will not make a complete circuit or revolution as quickly as the sheaves. Because of this, belt frequency is always subsynchronous energy. An equation for calculating the belt frequency requires you to know the diameter of one sheave, the speed of that shaft, and the belt length. For example, an 11-inch sheave turns at a speed of 1780 RPM, and the belt length is about 112 inches. Running the equation yields a belt frequency of 549.22 RPM. This is about 0.31 orders of shaft turning speed. The third harmonic is near the shaft speed, which can add to the 1 times energy if the resolution is not adequate. Maintenance software packages such as CSI's Master Trend have programs that calculate the belt frequency for you, storing the belt information of particular machines in a belt database. To calculate the belt frequency, you must know the diameter of both sheaves and the center-to-center distance. The sheave diameter needed is the pitch diameter. The calculation can also be made if the sheave diameter and the length of the belt are known. The output frequency can be in orders, CPM or Hertz. The primary belt frequency seldom appears, but harmonics are common. For example, in a 2-sheave drive, the second harmonic is pronounced because the defect bumps both sheaves during one complete circuit of the belt. In a multiple sheave system, the dominant harmonic of belt frequency is equal to the number of sheaves in the drive that the defect contacts. It is very common for a multiple of belt frequency to be very close to the turning speed of one of the shafts, so that it looks like 1 times peak. Analysts often mistake this as a balance problem, but balancing proves to be futile. A high-resolution spectrum of 800 lines and an Fmax of 3 times the turning speed of the high-speed shaft separates belt frequency from the turning speed peak. Here the assumed unbalance is in reality a 2 times belt frequency peak with an amplitude of 1.2 inches per second. The 1 times turning speed peak is only 0.126 inches per second. The belt problem accounts for more than 85% of the total energy in the spectrum. This measurement is from the inboard horizontal position on the motor. Belt defects are usually most dominant in the radial direction rather than the axial direction. An exception to this is when there is severe misalignment and the defect is on the side of the belt so it contacts the edge of the groove while at the same time pulling the sheave. The most often ignored belt-related vibration source is belt strand resonance. Belts, like any other component, have one or more resonant frequencies, and that resonance can literally destroy a machine when it coincides with another resonance or a fundamental frequency, such as shaft turning speed. The belt strand is the free or non-contact length of belt between the sheaves. V-belts are particularly susceptible to excitation of belt strand resonance. As the belt exits the sheave groove, it is held tightly by the sheave sidewalls as long as possible before snapping straight. This snap excites the belt strand into one of its resonant modes. Both the tension strands and the slack strands are excited by the snapping action. The belt strand resonant frequency can be measured when the machine is not running by mounting a sensor to the belt with tape and lightly tapping the belts. Since the drive is not running, both the tension and slack side will have the same frequency. In a running state, however, the tension side will have a higher frequency and the slack side will have a lower frequency. The difference can be 2 to 3 hertz between them. A vibration at belt strand resonance may have a wide skirt since the two resonances are so close together. A very real danger exists when the belt strand resonance is near another primary frequency, such as a shaft turning speed or a system resonance. The two frequencies may generate a beat which can be high enough to destroy the machine. A solution to this problem is to replace multiple V-belts with a single banded belt, which will have a different resonant frequency and may move it away from the other frequencies. A case history is of a belt-driven fan, where the belt strand resonance was at 28.5 hertz. The resonant frequency of the fan base was near the same frequency. An extended time waveform shows that the beat of the two frequencies produced amplitudes of a 16-inch per second swing. The fan eventually destroyed itself. Eccentricity is the condition when the center of the sheave is not the center of rotation. It can be caused by the shaft hole being bored off-center or from poor machining tolerances. Whatever the cause, the effect to the belt drive is that one sheave seems to be oblong or egg-shaped. As the shaft turns, the distance the belt travels shortens and lengthens. The belt tension continually cycles from slack to tight, causing the belt to snap each time the tension increases, exciting belt strand resonance. When measurements are made in line with the direction of belt travel, another characteristic of eccentricity is evident in spectral data. Peaks at both shaft speeds will be present, but the dominant peak will be equal to speed of the shaft with the eccentric sheave. In particular, the eccentric sheave will produce higher amplitudes on the opposite shaft. Machining tolerances for runout on the sheave diameter can be up to 10,000ths of an inch. Coupled with belt discrepancies, the total runout could be as high as 30,000ths. This runout has the same effect as an eccentric sheave. Axial runout or wobble generates axial motion in the same way that misalignment does, because the belts ride up in the groove and pull on the shaft. Wobble has the same spectral characteristics as sheave misalignment. Another source of belt-related vibration is a sheave loose on the shaft. Even when the sheave is keyed on the shaft, it can be loose and generate substantial vibration. The spectral data will have shaft speed harmonics similar to other mechanical looseness conditions. When these 6 sources of belt-related vibration are corrected, your belt drives will run smooth and quiet with a much higher efficiency. The next section illustrates how to check for and correct these conditions while installing belts to eliminate belt-driven problems. Correcting belt problems requires much more than just replacing belts, but includes making checks on sheave conditions, sheave alignment, belt tensions, and recording belt strand resonance. Here we show how to make these checks and corrections, as well as belt installation techniques on industrial machines. The vibration measurements made prior to balancing this fan had high axial energy at shaft turning speed. The belt guards were removed, and a quick inspection was made of the belts while the machine was running. Some of the belts were slipping, causing them to turn at different speeds. This was expected since misaligned sheaves causes some belts to be tighter than others. When the machine was stopped, the belts were inspected, and although they showed wear, the decision was made to reuse them. The alignment check was made on the sheaves using a string. They were misaligned about 1.5 inches. A straight edge can be used to check alignment, but a long straight edge just won't fit in a toolbox as easily as a 10-foot long string. And the string performs the job just as well when care is made to ensure that the string is not bent around a sheave edge. Aligned sheaves should have all edges of the sheaves in line and touching the straight edge so that when a light is placed behind it, no light comes through. If even one edge is not touching the straight edge, the sheaves are not in line. On this fan, the alignment could not be corrected by moving the motor only, but required removing and reinstalling the sheave. When replacing belts, check the sheaves to ensure they are in good condition. Check the grooves for rust and dirt, cleaning them with a stiff brush. Dirty sheaves substantially reduce belt life by abrading the belt. Then inspect for nicks or gouges because they can cut the belt. Wipe the grooves clean of oil and grease because they attack the belt materials. Use a sheave groove gauge and a flashlight to check the grooves for dishing or abnormal wear. Misaligned sheaves may wear more on one side than the other. If any clearance is visible, the sheave should be replaced. A new belt placed in the sheave should be flush with or above the outer diameter of the sheave. If the belt is below the outer diameter of the sheave, it is worn too much. However, this check alone does not ensure the sheave is not worn. If the sides are dished, the bottom corners of the belt may hold the belt out, but will wear quickly and work down in the groove. The best method is to use a sheave groove gauge, checking each groove, and then replace a worn sheave. When a sheave needs to be replaced, replace all sheaves in the drive, which increases the life of the belts. When using single belts and a worn sheave, they will seat individually and still have some pulling capacity. However, when a banded belt is used in a worn sheave, the belts all ride the same and cannot seat, which yields zero torque. In most industrial two-sheave applications, the motor is the movable component, while the driven unit is fixed in place. Rough align the motor in the center of its adjustments. This allows you to move it any direction after the sheave is mounted. Position the sheave on the shaft and rough align it using the string or straight edge. A taper bore sheave and bushing require extra care to be square to the shaft. The bolts should be just snugged up and the runout checked with a dial indicator to ensure that the sheave is square to the shaft. Place the dial indicator on the side wall of a groove and not on the face of the sheave. The face is usually not machined and may not be parallel with the groove walls. Tighten the bolts a little at a time so that one side does not pull in more than another, causing runout. Check the groove walls again to ensure the sheave is square with the shaft. Now the sheave can be checked for radial runout or eccentricity. This should be checked before the final positioning of the motor. If the sheave is eccentric, it is better to know that now than after the final positioning. Now the belts can be installed and the final alignment can be performed. When installing the belts, the movable component should be moved in so the belts can be placed on the sheave by hand and without prying them on. Prying the belts on breaks the wrap, the reinforcing fibers and reinforcing cords, severely reducing belt life. These belts should be discarded. Position the motor laterally so the sheaves are aligned, and if your machine has adjustment bolts for lateral movement, secure them as a guide. Verify that the alignment is good, rotating the shaft to ensure the sheaves are true. On multiple belt drives, adjust the belts so that they are all positioned with the slack side on the same side. As the tension is adjusted, the belts will not be able to slip, but will pull against each other and may damage the belts. The next step is to adjust the motor out until the proper tension is set. Be sure to turn the adjusting bolts the same amount so the motor moves straight back, keeping the sheaves in line. Too little tension allows the belts to slip and burn. Belt squeal is an indication of too little tension. Too much tension causes separation on the outside banding, leading to belt failure. The proper belt tension is the least tension that keeps the belts from slipping. This can vary for different belt types, belt speeds, sheave diameters, and drive configuration. And the tools to measure the tension can be very sophisticated, such as an ultrasonic sensor, or very simple, such as the rule of thumb. The long-standing rule of thumb has been to press on the belt with your thumb and measure the deflection, which should be about 1/64 of an inch for every inch of center to center distance. However, some thumbs are heavyweights and some are featherweights. An improvement on the rule of thumb is a small, inexpensive gauge produced by several belt manufacturers that measures the force applied and has a scale to check the deflection with a given force. Charts provide the recommended force for the various belt types and center-to-center distances. When installing new belts, set the tension 1/3 tighter and check it after the first few hours of running, adjusting it if necessary. Use a straight edge as a deflection guide, or in multi-belt drives, use another belt as the deflection guide. When the tension is properly set, make a quick check that the alignment is still true, install the belt guards, and start the machine. Be sure to perform all these steps, being as accurate and precise as possible to ensure a smooth running belt drive. The belt drive on this machine uses 3 belts that must drive sheaves on both sides of the belt. These are the double V belts. One belt is bad, having separated and lost a long section from one side. A sheave configuration like this puts tremendous stress on a belt because both the top and bottom side of the belt are subjected to compression and tension. For this reason, the reinforcing cord is in the center of the belt. These belts are size CC81. The CC refers to a double C size belt, which is measured on the inside. So this belt is 81 inches long on the inside, but is 87.4 inches on the outside. Only one belt is bad, but all 3 must be replaced. The other 2 are worn more than a new belt would be, and it is important to get a matched set, as variances in length affect the efficiency of the drive. Although belt manufacturers have much closer tolerances than they used to, there can still be some discrepancies from one run to the next. Some manufacturers mark the belts so you will know if you have matching belts. For example, the belts from this drive show the belt size, the manufacturer's name, and then the number 50. If a belt is 1/10 of an inch longer, it would be labeled 51 and so on. If it is 1/10 of an inch shorter, it would be labeled 49 and so on. Since all 3 of these belts have the same number, they are a matched set. Select a new matched set and remove the old belts. The tensioner is loosened enough to remove all the belts, and the new belts are placed on the sheaves without prying them into place. The tensioner is tightened and the belt tension is checked with a tension gauge. A few steps were left out of this belt replacement job due to time constraints. Some of these steps are: inspect and clean the sheaves. Check the sheave for runout, both eccentricity and wobble. And check all the sheaves for alignment. However, if the drive runs smoothly and with minimum noise, the sheaves may be in satisfactory shape and may be in alignment. The critical steps were performed. All the belts were replaced with a matched set. They were installed without damaging the outside wrap, the internal fibers, or the reinforcing cord, because they were not pried onto the drive, and the proper tension was set. Hopefully, this set of belts will reach the design life of 25,000 hours. Belt drives are normally considered to be the real shakers in the industry, but they're very economical, are fairly easy to maintain, can carry heavy shock loads, have a high operating speed range, and a high service life. When time is invested on the front end to ensure a correct installation, the return on the dollar invested can be a hefty payback. Inspect the sheaves for wear using a groove gauge. Check them for proper alignment and runout, including eccentricity and wobble. Use the belt that fits the sheave and that will carry the design load. When replacing a worn belt in a multiple belt drive, replace all the belts using a matched set. Set the belt tension, making sure that it is tight enough so it does not slip. Determine the belt strand resonance and compare it with system resonance and other forcing functions to ensure it will not be excited by them. Replacing multiple belts with a banded belt will change the resonant frequency and may move it away from problem frequencies. Record this resonance frequency for future analysis. Calculate the belt frequency, realizing that multiples of it are most likely to appear in spectral data. Use enough resolution so that belt frequency harmonics will be separated from other energy, such as turning speed of one of the shafts. Check and correct belt problems before doing other work to minimize vibration, such as balancing. Belt-driven equipment can run smoothly, but like other power transmission sources, it requires a conscious effort to overcome compromises and keep the machine in optimum condition. Although many areas have been covered, providing a solid foundation for successfully correcting belt-related problems, and although we've demonstrated best practices for single and multiple belt applications, we realize each belt drive is unique and may require other steps and techniques to produce satisfactory results. Thank you for joining the thousands who have recognized CSI as leading industry with quality information, instruction, and application of PDM and RBM techniques. Whether you use sophisticated equipment and methods or simple methods and equipment for minimizing belt-related problems, we are confident that the application of the tips and techniques presented here will dramatically improve your belt drive performance. We look forward to assisting you achieve success in your future endeavors.